So given this situation, we're starting to discuss Gabor multipliers. So multipliers, I mean, again, I'm comparing this with the situation of the audio engineer, means amplification and weakening or so. So the first thing will be the following. I'm saying I'm taking, maybe I'm changing it a little bit, well, what I'm doing here is a low 0 to 1 signal. That's the name of a little file that I'm using most of the time. And the command is I need an n by n function. So I need a function on my discrete phase space. So that's the format of my function. And I rescale it by 3. So that will be a function with values between 1 and 3. And then I add +1 because later on I would like to do the inverse. Now, 0, 1 means, of course, it's a real valued function. So what I really do is I say, well, I take a random polynomial, trigonometric polynomial, which is degree 3 in the horizontal direction. So I have 3 positive, 3 negative frequencies, so 7 time shift parameters. And north, south, up and down, I have 5, so I have 11. So I'm more or less creating 77 complex random coefficients in a 2x2 scheme, which are kind of plane waves, if you think of this. And these things will be made real. So I take the real part, that's still a trigonometric polynomial. So it's something which is not changing too much, but it can be used. So that the point is, if I sample this at different lattices, the values are realistic, and you see the new version has values between 1 and 4. And this is what we will use. Now, I will describe you how Gabor multipliers are described in a naive setting and then in a more complex situation. First of all, I'm saying, well, we have these weight functions, and I mark with my SPI command. So this is SPI centered in the same way as my image is centered. So 0 is put in the middle. That's not the data structure, but the way how we visualize it. And SPI's hold is the H here, and in black. So with black dots, I've marked these 720 points of our lattice. And of course, only the values of our continuous weight at the lattice points will play a role. So I just say, well, what are the condition, the numbers? Recall that row num and column number of this, you could also do this. I don't need it now, but I just for your convenience. This would be in case you want to know the row numbers of your lattice points, and it would go with row number 1, column number 1, row number 17, column number 1. And for example, this point here, the point which you would label as 1, 1, because this is 0, 0 in the real life situation, that would be row number 17 and column number 21, which is 20 to the right of the first one. So these numbers can be also drawn if you need it for something. But if you do this, it just goes through and counts from 0 to n squared. All the points which are marked have a number, and the length is, of course, 720 of this. And then I'm saying, well, I can use a routine, and we'll hopefully can talk about the routine. It's Gabor multiplier in the version of Mario Hampeis. So MH is for the name of the person who has done the last efficient implementation. And what are the ingredients? Now, one version, that's the one that I'm using at the beginning, is to say, well, I have a weight defined everywhere. I have already the idea that I use a tight Gabor family with A and B. So I'm using the tight Gabor window that we have looked at before and with A and B. So this is a sum operator. So clearly we could say this is a nice operator. And of course, it's a matrix of size n by n. And we could do even the eigenvalue, GMB and GMB is the eigenvalue. So I take the sorted routine I think we have done something like this before. It's just interesting to say what is the minimal eigenvalue of the new routine and what is the maximal of this new routine. And then it should be in the range of 1 to 4. No, well, it's, yeah, I think. Yeah, this is a bit strange, but I'm sure this has to do with the redundancy or something like this. I see that I have to correct it in the final message that you will get. So I put it away, but it's a kind of not good to do such an improvisation here. Okay, so however, what we can do is to say if we take that was the statement before. If you take constant 1, my symbol is constant 1, then you get the identity back. And yeah, I see what the problem was. GMW. No, I don't see the problem. Yeah. Then here, the alternative input would be that I'm saying I just give the matrix of the values here, which is the same format as the STFT, and I would say we are just doing a synthesis of this sampled weight and with the tied atom. Of course, here we know the system knows the format A and B, so it knows the lattice constants A and B and can use it for the synthesis in the same way as at the beginning, where you have the the weight everywhere, but then the sampling is done over the lattice A and B. Now, there is something wrong here. You see here, the old command was this. Yeah, probably I was, let me see, the change of the weight was, yeah, I think that was the problem. So I can reactivate it. I have changed the weight and I was not rerunning the code here. Let me do it once more with the new weight. And then let's see, that should work. Yeah, you see here. Now everything is correct. So it was just, I was using it, the old weight, which was in the range from 0 to 1, and now we have the range. It's clearly in the interval from 1 to 4. And so monotonicity, bigger symbols give bigger operators in the sense of positive operators. And also here, the reconstruction is perfect. And the input could be also done, and you see it's really identically on the operator. Now here is nothing to be done, and therefore let's recall that we have this landscape of lattices. So bar-lat is giving me a variety of things. I should say that this has been done with a minimal redundancy of red 1, a maximal redundancy, and a maximal eccentricity. And this is so very close to 1, or maximal redundancy 3, and eccentricity 3. So all the red and the yellow points correspond to lattice constants, which are on the good side. So the critical line was the pairs where A times B equal N. And because we had this comment, this is where you would use the Sachs transform. You could, of course, have sublattices of this. And now, okay, now I'm rerunning this part here. We're looking at the different possible Gabor multipliers coming from these lattices. I'm not doing it completely systematically, but I'm just recalling here. You see again the same, and another weight with the same routines. And what you see here is I could do, yeah, I could do the continuous, no, what I would call a short time Fourier transform multiplier. So what is the analog of the continuous case? That's the situation that you have A equal B equal 1. So you take the full matrix weight function, and the redundancy of this is you have n squared pixels in your phase space, so you have divided by n, and because my window have norm 1, you can expect that in this way you get identity if you take constant 1. And of course this is, maybe I'm doing this also, comp norm Gab mul mh with ones of n and g divided by g, divided by redundancy. Or maybe I just take this as it is and say, well, how is it compared to the identity operator? And the answer should be, this is exactly n times the operator. Now, the AW is written, the symbol is chosen to be the so-called Anti-Wick operator. So in the continuous situation, you would say, well, there's a distribution, a function, a generalized function on phase space. And while you're multiplying a smooth, continuous short-time Fourier transform, which is a square integrable for a square integrable function, afterwards you get something which you still can put back to the signal space. And that's what you do here. So you're doing the full thing, and in order to have the right normalization, I divide by the redundancy of the full lattice, which is n. And now I'm comparing this with the Gabor lattice with the same weight and with lattice constants 4, or with lattice constants 3/6. And what you see here is these numbers, maybe I'm doing it in the opposite direction. So the AW is already in the normalized version, and the other ones with small lattice constants, and you can vary it now. It's just up to some number, which is the redundancy of the lattice with lattice constants n/3. So maybe we check this also, 3/6, 3 times 6, which is 18. And here we should have n divided by 16. Okay, this is what we see directly, but and you see this is the same number here, and the arrow is very small. So after rescaling, it's 10 to the -9. So that means whether you're taking a Gabor multiplier or a Gabor multiplier with, I mean, a continuous Gabor multiplier, or a discrete Gabor multiplier with the lattice, if the lattice is fine enough, and of course, if the symbol is smooth enough, it's called an upper symbol or Bayesian symbol for the quantization of operators, then everything is fine. Now, the next thing that I'm doing here is, once more, I recall that these things have positive operators with operators eigenvalues in the range from 1 to 4. But here you see a little bit better how the eigenvalues are compared. We could try to show that this is related. Maybe I'm doing this also here to the histogram of the weight function, and maybe I try to make well, maybe 40 values, hoping that it's running not too slow. But okay, well, this doesn't show too much. You would have to take the cumulative sum to get this in the reverse order. So yeah, I'll leave it out to you. But essentially, if you have a function which has one big mountain here, then you would see that corresponding to the area of this big mountain, you'll see big eigenvalues, and in the rest, if the rest of the territory, which may occupy maybe 80%, and 80% of the eigenvalues will be quite small. So assume you would take a step function, for example, then roughly speaking, the area where you take certain values is giving you an intuitive approach to the eigenvalue distribution. Maybe I should also do this here. But what we can try to do here is to check what we can do with the inversion of an operator. So somehow my story would be the following: some guy is doing a recording with classical music, but he is a rock fan, and he is changing the amplitudes of different frequencies at different times. Now assume that I'm able to watch the person, which means he's building a Gabor multiplier with symbol W, and I try to undo. So I want to get back to the original recording. And of course, when he is multiplying with 1.5, I would reduce everything by 1.5. So in our case, that means we have the inverse in the pointwise sense of the multiplication operator on the phase space, and we have the Gabor multiplier, again normalized appropriately, coming from the pointwise inverse. But we can also say what we have seen. This operator has eigenvalues between 1 and 4, so it's definitely invertible. So we can take the inverse of the operator. So we have two things, and roughly speaking, the coin game is to which extent is pointwise inversion of the weight function the same as inversion of the operator. And if you look at these numbers here, in our concrete case, it looks quite good in the sense that the operators have almost the same norm. So the quotient of the norms, and again taken in the Frobenius norm sense, so it's just in the matrices in the Euclidean sense, or as pixel images if you want, with the sum of the square of all the entries and the square root. So they're almost the same norm, but even if you normalize them, the error between them is just in the third decimal. So you see, you get, in this particular case, you can get almost the same operator. Now, you have seen that starting from this weight, or maybe going to this first weight, we're sampling at the lattice points, and now you can argue, well, what can I say quantitatively about this error? So how much is the smoothness of the weight function playing a role? Because if you're having a function which is not smooth, it may depend very much on the lattice that you have here. Or you try to build a function if you're allowing a big smoothness, I mean a large variation of smoothness of this weight. Maybe you're getting quite different operators by just sampling at different locations. You can do the same thing by saying, well, but at the end, you can take, you can try to figure out the smooth version of your weight function and sample that. And you will see that smoothing at a rough weight is in the continuous setting is giving you almost the same operator as the original one. So that's another question that you can ask. Or you're changing the atom. You don't take the Gauss function, but you take a more narrow one or not so good one. But what I find always important is to try to compensate the error between, the error introduced by discretization through the Gabor family, which is an error which occurs even for constant symbol, meaning for the Gabor frame operator, by replacing the atom by the corresponding tight atom. Recall, there is a nice fact about this tight atom. Among all the tight Gabor atoms which you could use for this particular lattice, the GT that we have with inverse square root of the frame operator is the one closest in the L2 sense. So here in the L2 norms, discrete Euclidean norm, to this atom. So you can have many other tight atoms, but then they're further away from the original one that you would like to use. Okay, now here I have again computed the things, but let me just discuss. Yeah, okay, here is redundancy. Now that was just scrolling back. Yeah, let me just discuss one more aspect. And the aspect is the question. Sure, yeah, okay. I don't want to play around too much, but there is a routine that I have not yet prepared for today, which is called, can I do a best approximation of a given matrix by a Gabor multiplier? So you're saying you might be interested to approximate, and that's a nice task actually. You might approximate a given operator by a Gabor multiplier, because if you have a Gabor multiplier with a smooth symbol, then you can have a good approximate inversion, as we have seen by taking the 1 over. So in order to give you a background on this, I will tell you a little bit about the so-called compound condition number, which is related to the projection operators. So